Okay, thank you. Now I have to get used to the mic. Try my best so that everyone can hear it. So thank you, Lucio and Christiane, Veschi, for organizing the symposium. Actually, I feel very honored to contribute a few thoughts to this fantastic event. As Frei Otto and the very unique research culture he created here at the Institute for Lightweight Structures was actually one of the main reasons why I joined the University of Stuttgart in 2008. It is very difficult for me to not begin my talk on a personal note, so please bear with me for a moment. So the summer of 1975 in Mannheim constitutes a special moment in time for me, mainly because Frei Otto's fascinating multi-hall was completed for the Bundesgartenschau, as we all know, but also because just a few hundred meters away on the route of this astonishing aerobus at the time, the hospital was located where I was born in exactly this summer. So in my case, you can definitely speak of formative early childhood experiences during various visits to the Herzogenried, which is the park where the multi-hall is located. It was a structure to a young kid's taste. A grid shell boldly stretched into the sky, consisting only of the thinnest wooden slats, yet spanning large distances effortlessly with an absolute minimum of material. So the astonishing hall, of course, is still very impressive. So different in its appearance, so thoroughly large and free-spanning, and yet so light that you can read the shadows of the surrounding trees on the inside of its skin. So unlike many other youthful enthusiasms, this unique building has never lost its fascination for me, but rather sparked an ever-growing interest in this kind of architecture, and especially in the environment in which such an architecture was created, and of course, in this way, in the work of Frei Otto, who as an architect, as a researcher, and as a pioneer of lightweight construction has been a lifelong inspiration for me. Today, lightweight construction seems to be more relevant than ever in the view of multiple crises that the built environment is facing. Lightweight construction as a grander societal vision in the sense of Frei Otto, but also as a lightweight environmental footprint of an architecture that respects planetary boundaries. So taking the multi-hall as a point of departure, in my talk, I would like to offer a few lines of thought towards transformative architecture to, on the one hand, critically honor the groundbreaking work of Frei Otto and to expand his ideas towards our current work at my institute ICD and in CDC with many interdisciplinary collaborators, of course, first and foremost, Jan Knippers, who already spoke yesterday. Integrative design and construction is surely one of the key research streams that have evolved here at the University of Stuttgart over many decades, from Frei Otto's seminal Collaborative Research Center SFB 64 in the 1970s to the current Cluster of Excellence in CDC. So as aptly stated in the publication IL 25, the knowledge of the conditions under which forms emerge opens up the possibility of gradually rethinking the established separation architecture between design, the anticipation of reality in thought, and the production of buildings, the creation of physical objects. And I think this fundamental thought is as relevant today as it was during Otto's time. But of course, the methodologies of enabling a higher level of integration of design and construction have advanced significantly. I think we all agree that one of Frei Otto's most profound contributions constitutes his work on design methodology of form finding. And of course, at that time, form finding constituted a radical departure from the design methods that had dominated architectural design thinking since the development of descriptive geometry during the Renaissance times. Form finding questions the primacy of geometry and the related methods of form definition, which had been driven by the notation format of parallel and perspectival projections for centuries, thus limited architects to only being able to design what they could actually draw. So in contrast, form finding as a design method employs self-forming processes to derive form rather than defining it. In the case of the Mannheim grid shell, the famous hanging net model that you all know was used to physically compute the shape of the building. While it's also important to understand that there was a comprehensive digital model for the multi-hall, which was computed by the former Institute for Construction Geodesy, not the IL. The more significant relation to today's computation design can probably be found in the general definition of form finding as stated by IL researcher Siegfried Gass, who said that the characteristic form of an object found in each case is the result of the organization of matter in space, the joining of individual parts to form a new whole according to defined principles. In the organization process determined in this way, the part finds themselves in a state of equilibrium. The characteristic form of the object is the expression of these processes of formation. Based on this notion, I think today we can again radically extend the design method of form finding towards computational form generation by expanding the principles acting on the model, by integrating multiple design and performance criteria, and by informing the individual behavior of its parts across scales. Or in short, by lending the model's constituents multifaceted agency and the capacity of self-learning in an open-ended form generation process. I think the profound step forward here is that these design methods remain open to human design steering at any moment in time, no longer rely on predefined ordering systems, and thus generate topology, not only geometry, negotiate various often conflicting design and performance criteria, and directly integrate with and connect to new fabrication processes, which can be developed concurrently and in direct feedback with the related design methods and building systems. So I think this enables the effective production of finely tuned, load adapted, and thus geometrically unique building elements, resulting in novel structural typologies, such as segmented timber shells, which can be assembled like a three-dimensional puzzle in space, as we have shown in the Buga wood pavilion for the Bundesgartenschau in Heilbronn. So this segmented timber shell is actually only 160 millimeters thick, spans 30 meters, is built from timber only, providing kind of multi-purpose event space, not only with a roof envelope, but also excellent acoustics and a unique architectural experience. In a subsequent project, which is actually a permanent building that serves as an ideas laboratory for the Cluster of Excellence LIFMATs at the University of Freiburg, we were able to show that this integrative approach towards segmented timber shells not only results in a lightweight structure, in this case weighing 27 kilograms per square meter for a fully insulated building envelope, but also an exceptionally light environmental footprint, reducing the global warming potential by more than 60% compared to a standard timber building. So beyond form finding one equilibrium state, here the methodology of co-design concurrently advances the development of computational design and engineering methods, robotic fabrication and construction processes, and the related novel material and building systems to achieve a higher level of integration. In this pursuit of a higher level of integration, of course, biology can serve as a kind of concept generator. As extensively explored in the research of the Institute for Lightweight Structures, in living nature, structure, form, and materials, as well as the related material flows and processes of formation, are always inherently and inseparably integrated. It's interesting to note that fiber composites are the building systems of nature, not pneumatic structures. That's just a side note. Most load-bearing structures in biology are fibrous systems in which the fiber organization, directionality, and density is finely calibrated with the occurring forces. The resulting high level of morphological differentiation, the related resource efficiency, is emblematic for natural structures, of course. But it doesn't follow straightforward rules of optimization. And today, with the help of advanced computational analysis, design, simulation, and fabrication methods, we can explore the underlying morphological principles that are very often very counterintuitive of such fiber systems in nature and transfer them to architectural design and engineering through the co-design of related digital fabrication methods. So for example, as you can see here, we have developed coreless filament binding as a novel construction scale additive manufacturing process. So here, fibrous elements are freely placed between two rotating winding scaffolds by the robot. And during this process, the predefined shape of the building component actually only emerges from the interaction of the filaments and does not require any mold or core, and in this way also avoids any production waste or material offcuts. So in this way, the fiber arrangement, density, orientation of each building component can be individually calibrated, performance-tuned, and architecturally articulated, but remaining directly producible. 60 such elements, made up from more than 150 kilometers of fibers, form the primary structure of this Buga fiber pavilion, which achieves a free span of more than 23 meters and is enclosed by a fully transparent, mechanically pre-stressed ETFE membrane. With 7.6 kilograms per square meter, including everything, the pavilion is, on the one hand, exceptionally lightweight and demonstrates how combining cutting-edge computation technologies with construction principles found in nature enables the development of truly novel systems. But I think, on the other hand, it's also what one may call a genuinely digital building system. Just something that, without that higher level of integration enabled by co-design, would be very difficult to envision, design, and actually make. We have also shown how these principles of fibrous construction can be explored in the context of multi-story systems. And for example, in our project Maison Fibre at the Venice Biennale in 2021, where all load-bearing walls and slabs were only made from fibers and offered the visitors the intense experience and spatial expression of a highly dematerialized structure, which I think points towards a novel material culture in architecture. In recent years, we've also done considerable work in shifting from the synthetic filaments, glass and carbon fiber that was used in the Buga pavilion, to natural materials, such as flax fibers, which have actually been used for the production of linen fabrics for millennia, and also used to be a regionally available resource here in southern Germany. In hybrid structures, such as the one we developed for the Flux Hybrid Pavilion in Wangen, the fast-growing natural fibers can actually significantly reduce the amount of wood needed, in this case almost 2/3, and thus address the growing concern of the land-use trilemma relating to natural materials. I think it's interesting to note that similar to Otto's architectural work, this not only results in effective structures, but also an expressive architecture with a kind of strange coherency across projects. I think this coherency is not driven by the desire to author a particular form language, but the underlying cohesion actually emerges from the strong methods orientation and research-driven approach. In this way, we consider actually in CDC the construction of buildings based on scientific insights as an important component of what one may call in vivo architectural research. Here, the building is not merely a demonstration or an evaluation, but it's actually a vehicle for research and concurrent two-way knowledge transfer, as you can see in the INCDC building that will be completed here on campus at the beginning of 2028, just a bit down the road, which integrates the research of the class of excellence in a large span segmented timber shell roof, a novel multi-story timber building system, radiant concrete foundations and slabs, as well as a large load-bearing natural fiber element. Now, coming back to the multi-hall, one particularly fascinating aspect of the project is, of course, that form finding here was not only employed during the design stage for physically modeling the shell shape, but also almost like an on-site construction method. As we know, the entire shell was constructed as a planar regular grid on the ground and then incrementally jacked up using scaffolding towers and a forklift. So once certain grid points had reached their target coordinates, the shell was locked by tightening the bolts at each node and fixing the perimeter in place. Today, the methodology of co-design allows us to move beyond this still very passive understanding of the material inherent in form finding towards active self-shaping processes. So here, the material can be programmed to take a shape entirely by itself. For example, here you can see a simple, straightforward spruce wood bilayer panel that is materially programmed, in this case, through the differential moisture content and fiber direction of the wood lamella to take on a predefined curvature during a drying process. It's absolutely regular timber. This method of material programming actually works really well because it leverages the hygroscopic properties of wood, and it works well on a construction scale. As you can see in these 23 meter long, curved, cross-laminated timber segments, which were produced in exactly this way, constitute the load-bearing structure of the Wangen viewing tower that you can see here. So the load-bearing structure is only the 130 millimeter double curved, single curved timber strips. So the resulting global hyperboloid shape and the local three-dimensional corrugation results in both a novel, highly resource-efficient timber structure and a distinctive architectural experience while climbing through this vertical timber tunnel towards the transparent viewing platform. The on-site form finding of the Mannheim Grid Shell was certainly intellectually beautiful, but it also exposed some of the profound limits of that method. In line with most other engineering methods, form finding is profoundly based on an idealized understanding of materiality. Materials are considered to be homogeneous, and their real-world characteristics are expected to perfectly match their abstract textbook properties. While this may be the case for highly engineered and industrially produced materials, typically with the downside of high embodied carbon and energy as a consequence, form finding as a design method struggles to deal with the material variability inherent in biogenic materials which Otto's team experienced firsthand in Mannheim. Actually, for the timber shell, initially the use of regional wood was considered, but after serious difficulties of achieving consistent and reliable bending due to the material inconsistencies and related breakage, long, consistent Western hemlock battens had to be imported from North America. So both the need for continuity of elements, the required homogeneity of materials, I think poses a considerable challenge to reconcile with today's urgent need for circularity and an increase of biogenic and reclaimed materials. So in order to develop structures that are not only lightweight, but truly effective in the way we use regional resources, we need to overcome this inherent redundancy of textbook properties and related standards for renewable materials, and instead lend the individual material agency as a design driver. We need to develop fundamentally new methods of capturing, understanding, and employing the biological variability of natural materials and the pre-use features of reclaimed materials in design and construction, which entails rethinking variability as a constructional benefit rather than a disadvantage, and directly connecting design and construction to the natural sources of the material. Before coming to an end, I will spend the last 3 minutes to highlight 3 other points, because I think it was not only Frei Otto's work that was visionary, but also his way of working. In today's frenzy for immediate innovation and direct impact, which I think is a syndrome of our scientific community, it is humbling to see how long the development of some of Otto's ideas took. Even if you just focus on the research demonstrators of timber grid shells, it took 13 years from the first prototype exhibited at a German building exhibition in 1962, the less known grid shell under the German pavilion's tent roof, to the construction of the Mannheim multi-hall. And I think it's also equally humbling to see or to understand that despite the astonishing idea, the resource efficiency and the structural beauty of timber grid shells, only a handful have been realized since 1975. This is still the biggest one. So the real impact here in my eyes is not the structural typology, but the pioneering methodology which influences design and engineering thinking to this day. Probably even more importantly, Otto's Institute IL created new constellations of actor networks in architecture, engineering, and construction. While for many buildings that today we refer to as Frei Otto projects, there was always a specific architect and engineer, but his kind of middleman role as a creative driving force and lateral thinker had a decisive impact on the project outcome. And I think this is the important point, forged new collaborations across architecture, engineering, and natural science, which still constitute the roots of the unique interdisciplinary research culture at the University of Stuttgart that still thrives today. Of course, it's absolutely impossible to understand the work of Frei Otto and his impact without contextualizing it in the spirit of the time. And I think it's also important to understand that the 1970s were certainly not the early 1970s. This again contextualized against the multi-hall. Were not carefree times. Were characterized by multiple economic, political, and energy crises, as well as the beginning ecological concerns. But somehow, societal expectations, its optimistic imaginaries, and thus also the results of actual public architecture competitions seem astonishing from today's point of view, which is probably most evident in the way Frei Otto actually got involved in the Mannheim multi-hall project. So here you can see the competition entry for the multi-hall by Karl Fried Mutschler. He envisioned a membrane suspended from floating hot air balloons and won the competition. I mean, how unthinkable would that be today? So only when the building authorities actually declared themselves not responsible for floating structures and air traffic control did not know how to deal with it, Frei Otto was actually called in to develop an alternative lightweight structure as a grid shell. So I think today it seems we as societies somehow struggle to have the ability or at least the confidence to see the great value, wonder that lies in the rigorous scientific pursuit of what initially appears to be absolutely crazy ideas. In that sense, Frei Otto remains a great inspiration to this day. Thank you.